Hello, my name is Benjamin Hsiao. I'm a distinguished professor of chemistry at the Stony Brook University. I've given this talk on behalf of my team, especially I want to thank Dr. Priyanka Sharma and Dr. Tom Lindstrom as valuable team members of this talk. The title of the talk is Upcycling Biomass Waste as Effective Water Purification Materials by Nitro-oxidation process. But before I start this technical part, I want to also say a special thank you to the Prince Sultan bin Abdulaziz International Prize for Water, the Creativity Prize this year. My journey begins with water purification by using synthetic nanofibers for water purification. This is one of the products that my initial technology made, that we made a water bottle that can use gravity to filter out most of the pathogens, including bacteria, viruses, and some contaminated metal ions by just simply gravity using the combination of filtration and absorption. And this product actually won the 2015 TechCrunch prize. However, during my extensive traveling to different places, especially like Africa and sub-Saharan Africa, that in this arid environment and people cannot afford the products that I invented, which laid the ground of my next journey. That's the process of this natural oxidation process. So let me start by introducing a new class of water purification materials. That's nanocellulose. Nanocellulose can be extracted from any biomass. They can be used as absorbent, membrane materials, fluctuant. They can even support catalysts for photocatalytic reactions, as well as they can support disinfectants. And however, traditional way to make this nanocellulose out of biomass feedstocks involves many steps. Typically, this nanocellulose can be derived into two classes. One is the top-down process, means that you use your feedstock, you use chemistry, and you treat them, and to break them apart into nanoscale. Another way is the bottom-out process, means that you take sugar water and you use fermentation and bacteria to make them into nanocellulose. What caught my attention is actually by the combination of chemistry and very little mechanical energy involved. For example, it has been demonstrated that if you use a tempo oxidation process, you can modify the surface of cellulose. Therefore, you can use very low energy to defibrillate this into nanoscale. Compared with the rest of the process, this one seems to have the lowest mechanical energy that's needed. And I thought to help the people living off the grid, perhaps the lowest energy is necessary because they don't have grid to provide large energy. And the chemistry that this will work is, this is a typical building block of any biomass, which we call this elementary fibrils. And on the surface, and their cellulose molecules, and they consist of this hydroxyl group at the C6 position, and tempo oxidation can oxidize in this hydroxyl group and convert them into carboxylate group, and eventually this will be a charged species in the presence of aqueous conditions. So this will be minus position. However, tempo chemistry is relatively expensive and it's not environmentally friendly. So if I were to use tempo chemistry to defibrillate any biomass, and just imagine the I need to recycle these tempo agents. I need to produce a lot of this tempo agent. So they're not truly a sustainable approach for water purification. So our lab has developed a very simple process. It's called nitro-oxidation approach. Simply, we use two major components, that's nitric acid and sodium nitrite, to extract this nanocellulose from any biomass. And both components are major ingredients for fertilizers. So our chemistry is related directly to fertilizer making process. And this is a pathway how this chemistry will work. So actually, if you compare our process by nitro-oxidation method, which we can treat any raw biomass, we simply have one simple step. We can get nanoscale cellulose compared to the previous method, like tempo oxidation method, that the steps is drastically reduced. That's because we do not need to pulp the materials. Pulping means to remove the lignin compounds. We do not need many steps, therefore, to generate the same material. So our method basically combines the steps of pulping and cellulose oxidation, therefore saving the energy and water and chemicals tremendously. Actually, if you look back in history, people in the 1960s actually already started using the nitric acid pulping process, try to pulp wood feedstock. They were not successful because wood is quite dense and it does take high costs for pulping process, and the nitric acid is relatively toxic. But the idea of after the pulping, the spent liquor or the effluent can be converted back to fertilizers has been demonstrated. So this is actually a very good motivation for us to learn what has been done before. There is another process, that's cellulose oxidation process. As you know, that to make nanocellulose, one needs to combine the pulping and cellulose oxidation using nitrogen dioxide or NOx to oxidize cellulose is also well known. Even today, we're using oxidized cellulose as biomedical products. This process was first demonstrated in 1940s or so, and the product can be used for wound healing and all kinds of biomedical applications. So therefore, the combination of pulping and oxidation is actually quite ideal to directly extract nanocellulose from many of the underutilized non-wood plants. As we know that all the biomass feedstock, besides food, wood is probably one of the most valuable materials. However, even with food crops, we only take a very small portion of it. The rest of the residues, as well as many invasive species and things that we don't use, the tremendous underutilized feedstock resources. So this natural oxidation method is particularly suitable to extract nanocellulose from these materials because number one, They have very loose structure. Number two, they also have very small lignin content. So how does this work with this nitro-oxidation method? Number one, nitric acid, as we all know, that is a strong acid and strong oxidizing agent. They can easily degrade and therefore dissolve all the lignin content. And plus, nitric acid can decompose the hemocellulose and also remove the hemocellulose part. And plus, they will generate NOx to oxidize the surface. So if you look at all the chemical composition of all the just agricultural residues, you will find out all the lignin contents are pretty low, so they're ideal feedstock. So this nitro-oxidation method turned out to be an ideal process to actually extract nanostructured cellulose materials and make them into very effective water purification materials. So just to demonstrate the case that we use agave. Agave is quite abundant in Africa, South America, Mexico, even in the some part of arid environment in the United States. We just choose some agave at the Stony Brook University campus. We simply use this for landscaping, but in the winter, and we collect them as waste materials. We use this as a feedstock, and we use our nitro-oxidation method, and then we can extract very high value nitro-oxidized cellulose nanofibers. They looks like a gel, and the fibers has a very small thickness and very charged content, and they're negatively charged. So they're very good absorbent materials. Furthermore, we can recycle the effluent into nitrogen-rich salt. So this is effluent neutralization process, and the final product is actually a salt. This is effluent. The salt, this is nanocellulose in suspension. They actually can be used as a wonderful nitrogen enriched amendment as a fertilizer for crop growth. And this method turned out to be quite universal, of course, for extracting of all kinds of biomass, to convert all kinds of biomass into nanocellulose. For example, we use sorghum stalk, maize, beanstalk, millet stalk. And of course, the detail of the extraction is a little bit different. And they're really, the process is very similar to extract DNA fibrils from all kinds of animal feedstock. So, and we have successfully extracted nanocellulose from 16, and this list is growing kinds of raw plants. And the materials turn out to be ideal absorbent materials. They behave like a flocculant or coagulant agent to remove all kinds of metal ions. For example, we show you cadmium, lead, even uranium, different type of heavy metal ions. That's because typically this type of metal ions have plus charge. They're monovalent or divalent or trivalent. And the higher the valency, they form as a cross-linking agent to bond to negatively charged suspension of nanocellulose. So they would gel, and after the gel, you can easily use any filter, microfilters, using gravity to remove them. Furthermore, we decide to tackle one of the major waste water source, that's nitrogen removal, and to upcycle them into fertilizers. So typically, we generate tremendous of nitrogen waste in the form of ammonia, eventually convert into nitrate. So this is a nitrogen cycle, typically in our environment. And we decide to just do a demonstration using nanocellulose to intervene this ammonia. So we have designed the experiment using the cellulose-based absorbent to actually absorb the ammonia, because ammonia in the water is +1 charge, and this is -1. So actually the absorption of ammonia attached to this, they can be actually also used as amendment for fertilizer. So we have demonstrated this cellulose is absorbent for ammonia removal and recovery, and this is after the coagulant with ammonia. And this is the performance, that's ammonia removal efficiency at different concentration. Through this, we can estimate the maximum absorption capacity of our nanocellulose against ammonia. We have compared this with all kinds of existing published data, and we find out the removal capacity is relatively high. It's probably one of the highest ones. And after we remove the ammonia, and this ammonia absorbed nanocellulose, whether it's in a microfibers form or nanofibers form, they can be reused as a fertilizer or even soil amendment and for agricultural growth. So we have compared a starter and with our ammonia absorbed microfibers or nanofibers with control without anything. We haven't seen it can help the crop growth property. So this gives us a different type of upcycling or circular designs to upcycle all the waste, including agricultural residues, biomass waste, and combined with wastewater stream to absorb ammonia. Therefore, we can generate fertilizers and shorten this circular economy. We can further apply this technology to even aquaculture. This is a fish pond. One of the major problems with the fish pond is nitrogen generation. We can create a new type of cellulose absorbent to absorb all the nitrogen and convert this into a fertilizer to promote the crop growth, and therefore really having a more sustainable circular design to promote the nexus of food, energy, and water. So, and finally, I wish to dedicate this talk to my entire research team. This is a picture of the team taken in 2019, and last year was a difficult year because most of the students cannot come to the lab. We have to work remotely. So this prize is really belongs to my entire research team. Again, this is a picture of Dr. Priyanka Sharma. Thank you very much.